look at the small scale dynamo, so avoiding the mean field dynamo, fortunately. So we're going to be looking at a weak seed field in a random flow, and I've got here homogeneous isotropic turbulence, which is what we're going to be modelling. If we're doing things properly, then we'll be looking at a solution to these two equations, which fortunately we're not going to do. And if we were doing that, then we'd have to be using a large computer, big numerical schemes. We could get clever and use LES or some sort of subgrid modelling, but then we've still got the problem of being grid-based, and if we want to do something Lagrangian, which we do, we've got to interpolate between these grid points. We could use a toy model, so that's an option. But what we're going to look at here is the KS model, which some of you may have seen before, some of you may not, where we're trying to make a toy model a little more realistic. So we're looking at multiple scales, and we can impose a spectrum. So we define our velocity field to be the summation of random Fourier modes, and we have a choice over, importantly, the wave vectors here, and EK, the energy spectrum. And we're going to impose, for all this talk, a minus 5/3 spectrum, but we could vary that, which is one of the useful things about the KS model. I've just got here a picture for you of a slice through KS and DNS with the same Reynolds number, and this highlights key differences between them. So both are random fields, but we can see here there's a lot less structure in the KS model than the DNS, and you see the same thing if you take isosurfaces. You don't see these nice filaments of vorticity. It's a random field. The other problem is with KS is that you don't have advection of small eddies by large eddies. So with these this summation of Fourier modes, these modes are fixed. So that's another thing that we lose. But so our choice of the wave vectors and the wave numbers is quite important. By choosing them isotropically, like this, over a sphere even, we get our homogeneous isotropic field. Through choice of different wave vectors, people have looked at rotating turbulence and stratified turbulence. In particular, Frank Nicolai in Sheffield's been doing that. And as I mentioned previously, we have control over the energy spectrum, which is useful. What I've got here is just quickly to show two-particle dispersion. So the KS model's mainly been used by atmospheric people who've been looking at Lagrangian statistics in turbulence. And here we have two particles. These are averaged over thousands and thousands of particles, where we have our ballistic regime, an Ice-Richardson 3/2 law, and then a random walk. And it's typical of KS that Lagrangian statistics are reproduced well. Another useful thing is that by imposing 2π dependency on the wave vectors in each component, we can impose periodicity, which is useful, because we're going to want to eventually compare our new model to the induction equation. And periodic boundary conditions are easy, and through careful choice, we can impose periodicity. All the simulations that I show you won't be with the periodic flow, but it's something that we will be doing. Okay, so the main part of the talk is this new model. So what we're considering is how useful the induction equation is in a rarefied plasma. So you've got these magnetic flux tubes wobbling around, pulled around by the flow, but they don't know about each other until they're going to get very close. And how well can the induction equation model this when diffusion is acting over all length scales? So we're going to consider altering the power here of this operator in some sort of hyperdiffusive manner. And we've got here this paper, reference to this paper, where this was done with helicity. But it was shown that there was an important effect on the dynamo, and that the dynamo saturated at higher energy levels. So this is something important, but what we want to do is consider taking this to the extreme and considering these flux tubes wobbling about, but they only know about each other when they get very, very close. So the starting point for this is the line stretching experiment. So we're using the frozen-in theorem, and it's been used a lot by people with fast dynamos to act as an upper bound for the growth rate of the dynamo. But now I want to take it and make it more realistic. I've just got here a little scheme for how we model these lines there. It's just particles, fluid particles in the flow, and we have this resolution length, which is 2D, and as soon as we've moved past that, we introduce new particles. So that's just to keep the distant constants on these lines. There's some pictures later on that probably show this better. But now we want to consider what the action of stretching does to this flux tube. So we want to attach some flag, which we have a magnetic field strength flag, to each of the particles to measure what the action of the flow has done to the flux tube. So if we've got the frozen-in theorem, we've got BA's constant.
So A is not vector potential, right?
No.
Area.
A is surface area, yes. So we've got magnetic field times surface area is a constant. And if we've got the length of the flux tube times the surface area is a constant, it's easy to see that if we double the length, then the magnetic field strength has to go up by 2. So again, another schematic here, where we have our particles along this line, and these two guys get stretched apart from each other, a new particle is introduced. We can see the length of this is increased by 2, and so we alter these two flags here, which are our magnetic field strength flags. So all nice and easy. So testing this, we're going to use a nice, simple 2D model, which is this shear flow here, with Gaussian profile, and we're going to stick a flux tube straight down the middle. And fortunately for us, we can solve this analytically, and we get that mod B grows like this here, so it's pretty much linearly after some initial part. A quick picture here of what we get from the simulations. Like I say, it's all straightforward. We've got our initial flux tube here, and it gets pulled out into this by this Gaussian flow and this Gaussian shear flow. And I've just colour-coded here where we've got, as it gets lighter, there's more stretching, so it all makes sense. So there's very little stretching here and here. And what we're going to do is we're going to take a particle here where there's most stretching and plot the results from our model of B and what we get from the analytic results. And we can see it's not too bad. So here's the analytic result, so just a linear growth of B. And here's our particle, which is in the area of most stretching. And so there's this staircase where it oscillates around the true solution. But we've probably imposed the worst flow that we could do for this model, really, because it's in a random field, we wouldn't have just this continuous stretching at particular points where we get these sort of large discrepancies which are growing. We can see that it doesn't do too bad a job. Okay, so we've got these flux tubes, they're wobbling around, and we've said that something's got to happen to them when they get very close, so now we've got to do that. And this idea of modelling things via particles is used quite a lot in superfluid turbulence, where they take lines which represent sort of quantized vortices, and they evolve the particles according to the Biot-Savart law, and when these lines get very, very close, they reconnect. And so we've just pinched an algorithm straight from what we do in superfluid turbulence, modified it slightly because obviously these quantized vortices don't have directions, where our magnetic flux tubes do. So what have we got here? Just some details here. So we're looking at changing the topology of the field, and we're also looking at releasing energy from the system. Okay, so scientific here. So a schematic again of we've got our particles here along two flux tubes directed here, and we introduce this reconnection length d sub 0. So when these flux tubes get very close, pop the reconnection and energy is released, as we can see here. Going back to this, the reconnection scheme from superfluid turbulence, this could happen all the time because we've got no directions. And all we have to do is just be careful by monitoring not just this particle that are reconnecting, but particles close to it, we can tell whether the directions of the line are sufficient to reconnect or whether these two flux tubes are parallel and they won't reconnect. So, the preliminary simulations that I've got are looking really at the growth rates as a function of this reconnection length and some visualizations of the field. And one thing we're going to make use of is Gaussian smoothing. So, which I've just got a formula for here. So we're going to smooth these flux tubes out, and the main reason we're doing this is for comparison, because the eventual thing we want to do is compare this to solving the induction equation, compare mainly energy release rates, but also the morphology of the field. And through using Gaussian smoothing, we can do this. This is the initial conditions of the pick, and here I've just got lots and lots of loops, just an initial random field, and I've highlighted the particles on here, just so you can see them. So what we've got here, I don't know how well you can see it, is just a plot of log of line length against t for, I think this one's 0.2. So you can just see that it's in a pretty good exponential growth. So one with nothing much. And what we've got here is this growth rate plotted against the reconnection length. And if you flip this round, you could compare this to the growth rate for the induction equation, the same flow in another random flow, and it looks fairly similar. And did a log fit, and it looked pretty good. What here is a snapshot of later on in the flow. So I've removed the particles, or it just become a nightmare. See, it's pretty unclear here. We can see that things seem to bundle together. Again, using this colour code of red is the areas that aren't stretched, moving to yellow of areas that are highly stretched. And it's not really clear what's going on. And if you wanted to compare that to the field generated from the induction equation, good luck. So this is where we make use of Gaussian smoothing. And on the left-hand side, we have the field generated by smoothing the field that you just saw. And on the right-hand side, there's some simulations from Louise Wilkin, which was the periodic KS flow, and taking isosurfaces of both fields. And this is where I sort of hint at Anvar's talk, because we now want to compare the morphology of these two things. And we can see they both have filamentary structure, but doing that with our eyes is not very useful. So how do we measure the difference between these two fields, and also the difference between this field if we increase the reconnection length, if we look at different flows, and this is where Minkowski functionals are going to go in. So I'm not bothered putting any formulas up or anything because Anvar's going to cover it all. But what we can do is we can actually get numerical values from something which, judging with our eyes, is very difficult to do, to compare. Okay, so the future work that we want to do with this is, one of the key things we want to do is look at energy release rates and see if the dynamo driven by reconnections is a more efficient machine at converting mechanical energy into heat. We also want to compare morphology. Again, Minkowski functional is going to be useful. There's topological measures that we can look at. So we can look at curvature compared to magnetic field, point by point, and things like linking numbers, topological measures of the field. We also ideally want a nonlinear model. And the final part of my talk is going to be showing how we can, quite naively, introduce nonlinearity into the system. So, this part's okay. So we look at J cross B, and we can see here that we've got the magnetic tension, the magnetic pressure. If we kill this guy here and just assume these flux tubes look after themselves, that this pressure term goes, and we rewrite the tension in terms of a differential along these flux tubes. And here is where things get a bit dodgy, but we're going to use semipolar diffusion, which the idea of this is for rarefied plasmas, so the two things don't really go together because we've not got collisions. But it's just a way of sort of introducing this nonlinearity without solving Messier equations, and we simply modify the velocity field to the chaos model plus the J cross B term from the previous slide with some fudge factor here. Okay, when we do this, the nonlinearity works, so we get an initial growth, and then we get a saturation of this flux tube dynamo. And just to finish with, I'll have them moving. I'm not sure if it'll work or not. Nope. It comes with music as well.
This lasts a minute, does it, Emma?
Pardon?
It's the minute waltz. Does the movie last a minute?
I think it's longer. I think it loops. Right, let's see if this works. How do we go through this?
Very nice.
Okay. So we started off this. For visualization, it's easy to start with the small window. It fits quite nicely.
So how do you translate tension to music?
So the tension is included here, and you're going to see the effects of it coming up quite soon. So reconnections have created smaller loops, and here we can see tension kicking in. It drags us. Okay. I think that is the close of the talk anyway, but I'll just check. Yes.
Questions?
I have to say I'm a bit confused. Well, you're essentially solving the Cauchy problem, and then you're going to add something to reconnect the field. Is that right? So why don't you just solve the Cauchy problem exactly? So this was done in the 80s by Drummond and Horgan, but for this velocity field, why is it called the chaos velocity field?
Kinematic simulation is arbitrary
Okay.
combination of course.
Well, they take something, they solve the Cauchy problem, they add some noise, and they calculate alpha by doing lots of averages. It's a very, very simple procedure. But you can solve the Cauchy problem exactly. So I'm just trying to work out what it is, why you're getting such big errors. You know, this.
Yeah.
So it's not exactly Cauchy solution because you allow reconnection. This means
No, but the one he showed, the flow, the velocity, was no diffusion. There was just.
Yeah, there was no reconnections there.
Yeah, just trying to solve it.
It's just because Andrew inserts additional points, as soon as the separation of 2 points along the line exceeds a certain limit. And this regular flow, all the points simultaneously become too far apart. And too many particles are introduced simultaneously throughout the domain. This creates a step. In a small scale flow, such steps don't occur just because you're constantly introduce particles at small numbers throughout the domain.
David?
But because it's going in a step function, presumably this thing, you have to check the convergence of how many points. I mean, if you had a whole bunch more points, you would have got smaller steps. Presumably this thing is very dependent on how many points you have
On the resolution of the particles along the.
I mean, you have runs where you can make it, just as you would if you're doing a kind of regular disease, you need to check converge. You have we have convergence results.
I've not checked that. I mean, when it's with the small scale dynamo and with the KS flow, just the resolution's made to be much smaller than the smallest length scale in the flow. And when you do that and check, you get similar results.
Well, yeah, but what is the smallest length scale in the flow?
In the KS flow,
Yeah,
just 2 pi over Kn.
yeah, but I mean, for example, if you were doing a dynamo, and it doesn't have to be a very messy flow, you can think of dynamos that are more or less cellular. And then if they're a very high magnetic resonance number, the relevant length scale is something like R to the minus a half. I mean, and so it's minuscule, even though the cell size is like 1, whatever. And so, I mean, really, you'd want to say you could compare a simple flow with the induction equation.
But this is the advantage of this model. It's not the induction equation. The smallest scale of the magnetic field is D, which is under complete control of Hendra.
Yeah, I know, but someone...
This is a connection length.
Yeah, okay, so it's not the induction equation, but it's talking about magnetic fields moving in a flow. And so, you feel there should be some kind of point of contact with the induction equation. Sure, you can study this equation, say it's this equation, this is what it does. That's fine. But then is it what a magnetic field would be like?
Hendra, you promised next week, right? The results comparison with the induction equation. Of course, yes.
Next question.
Could this be a framework in order to describe magnetic fields in SPH simulation, where it's difficult to have a good description of the fields, and especially in order to ensure divergence be equal 0?
Yeah, I mean, as long as you have loops, then you always have divergence free, so that's easy to do.
Why do you need loops? Why can't you have open strings or flux tubes, which end at your boundaries?
Other questions? No.
But here we know that magnetic lines do not tear. They can follow. The divergence is preserved.
Yeah.
Here, quite comfortably.
Yes.
There is no doubt.
Well, until you let one of these strings end, and then the monotone drift.
Thank you again. The speaker is now.
Yeah.
Yep. So, we get a point here. Okay, before I describe imbalanced strong MHD turbulence, I'd like to sort of set the background by saying what I mean by balanced, weak, okay? Then I guess MHD turbulence, something that all of you know about. Okay. So, I'll probably take some 10 minutes or so just going over complete basics so that I can define things reasonably. Right? So that's something familiar to everybody. Incompressible MHD, that's a system I'll be dealing with. Two fields, magnetic and velocity fields, induction equation for the magnetic field, Navier-Stokes for the velocity field with Lorentz force. Right? So that's the basic system. I'll consider perturbations about a uniformly magnetized static state, okay, where this means velocity is 0. I have a magnetic field, a uniform magnetic field in the z direction, okay, and this static configuration is will be imagined to be sort of perturbed randomly, okay. So to study perturbations about the state, it's useful to look at a description of the same system using Elsasser fields, which are defined as linear combinations of the velocity and magnetic fields. These Elsasser fields, which I call W plus, W minus, are also incompressible. And when you stick these definitions in the induction equations and induction and Navier-Stokes equations, you get equations of motion for the Elsasser fields, which are very obviously symmetric. Okay, and it's very good to use these fields to look at perturbations about a static magnetized state. Okay, it's probably not useful for dynamos, where you're probably interested in converting kinetic energy into magnetic energy, but really useful for studying turbulence of a magnetized plasma. Okay? I dropped dissipative terms, okay, because the concern in this talk is with the inertial range of turbulence. So I wouldn't worry about stirring, I wouldn't worry about the dissipation range, dissipation scales, so somewhere in between, the inertial range. Okay? So just to note that in the uniformly magnetized state, the Elsasser fields are minus and plus VA z hat, where VA is the alpha speed. Okay? I'll just keep the alpha speed as a reference, I won't set it to unity. Alright, so we are looking at perturbations about static state. So I introduce perturbations small w plus and small w minus about the static state. Just stick them in the equations of motion, and these are the equations for the perturbations. Alright, with all the nonlinearity included, dissipative terms dropped. Okay. So before we look at the effect of these nonlinear terms, okay, I'd like to, it's really useful to look at what the linearized solutions are, something to be familiar with. Just drop these, you get linear equations for W plus W minus. These are incompressible, so the pressure can be eliminated by taking divergence of the whole thing. Right? Then we get something that is very familiar, alpha and slow waves. We have linear waves with W plus as waves of arbitrary, let's say, spatial structure, which translate uniformly in the plus z and minus z directions. Okay? Another way of saying it is that the plus waves have a dispersion relation where omega is proportional to kz, and the minus waves, negative waves, have omega proportional to minus kz. Okay? Useful to keep this in mind. The waves are, okay, I should define polarization at this point. Right? So let's say we're looking at it in K space. It's okay. Alright. let this go. So let's say I'm looking at a wave at a given k. The polarizations clearly in the plane perpendicular to k because the fields are have zero divergence. So in this, let's say the magnetic field is in the z direction. So I can choose two independent polarizations. The alpha wave is the one which is perpendicular to both z and k. It's sticking out to the board. And the other component which is orthogonal to this is the slope. Okay, that's a convention. Now it's important to distinguish between these because the alpha waves are mostly pointing in a direction perpendicular to z. Okay? And that will be important later on. Now, there are nonlinear analogues of the same thing using LSSM variables. For instance, you go back, sticking the nonlinear terms, and notice that if initial, let's say W plus is 0, okay, then W minus has an exact solution which looks like a solution for linear waves. It has arbitrary structure and it translates uniformly in the minus z direction. Okay, and vice versa. And this is very important. I think it's probably a fundamental insight of Craigman, okay, that because you have this property that a pure W plus wave, just translates this plus z direction, pure W minus into minus z direction. This means that turbulence, any kind of spatio-temporal chaos, can happen only when you have both W plus and W minus present. Another way of saying it is that there is turbulence when there's a collision between a W plus packet and a W minus packet. Alright? So much of the theory of incompressible energy turbulence is built on this observation of Craigman that turbulence is due to collision of positive and negative wave packets. And that's what I'll try to describe in the rest of the lecture. So there's this theory going back to the 60s, developed independently by Iroshnikov and Craigman, right, where this picture of collision between positive and negative wave packets is developed. Okay, let's just go over the phenomenology because it's important. Let's assume balanced excitation of positive and negative waves. By balanced, I mean that on average you have equal energy in the positive and negative waves. Okay? So they're stirred on some large scale L with amplitudes V sub L, which are sort of sub-alpha. So let's consider collision between a single collision between a positive packet and a negative packet, okay, of some scale lambda, which is much smaller than the stirring scale. So lambda is, let's say, an inertial range scale. Okay, in one collision, that's a perturbation. That a single wave packet undergoes. A plus packet just collides with a minus packet, slides by. But I want you to imagine a situation where the stirring is sort of homogeneous, okay, spread all over space. So after a single collision, the positive packet encounters another negative packet, and collisions keep building up. But these collisions keep building up with random phases. Okay, so the number of collisions it takes, let's say, a positive packet to get significantly perturbed is given by this random walk formula, which is V alpha n by V sub lambda whole square. V sub lambda is the amplitude of, let's say, a positive or a negative packet of scale lambda. Alright? And that's a quantity that we'd like to determine. It's an unknown. Okay? So after n lambda collisions, any packet, a positive or a negative packet, has been significantly perturbed. So we say that at this point, energy has cascaded from some scale lambda to, let's say, lambda by 2. So the cascade time is obviously the number of collisions times the time for a single collision. Okay, so we stick that in Kolmogorov's hypothesis of lambda independence of energy flux. That in the inertial range, there's a flux of energy going from stirring scales to a dissipation scale, and the flux of energy is independent of scale in the inertial range. Okay, so that determines B lambda going as lambda to 1/4. Okay, so this is the prediction of the Hiroshnikov-Kregman theory. Equivalently, there's a formula for the power spectrum. Now, it's very important that in this picture of perturbations building up randomly, that n sub lambda, which is the number of collisions, is larger than unity. Okay? Each collision is weak and it builds up randomly. So, since we know that, since we have a formula for B lambda, we just stick it in the formula for the number of collisions and find that n sub lambda scales as 1 over square root of lambda, which means that as energy cascades to smaller and smaller scales, the number of collisions it takes for energy transfer through scale actually increases, which means that a theory which you assume to be weak, okay, actually satisfies the criterion of weakness better and better as you go to smaller and smaller scales. So in some sense, the Hiroshnikov-Kregman theory at this level, phenomenological level, is very self-consistent. Alright? So, which also means that a self-consistent theory of a consistent theory of weak turbulence can be formulated rigorously using kinetic equations. I think Sergei used it yesterday. You would have seen kinetic equations in his presentation. Right? So once you have this kinetic equation, you know that the Hiroshnikov-Kregman theory should be described by three-wave resonant interactions, which means that the resonance condition should hold. That is, in every elementary interaction, K1 plus K2 gives rise to a wave with wave vector K3. Should also satisfy that omega 1 plus omega 2 minus equal to omega 3 plus. Okay? Only oppositely directed wave packets interact. So on the left, it should always be a omega 1 plus and a omega 2 minus, or vice versa. Alright? So you stick this in. Just look at the z component of this, add and subtract, then you find something remarkable. And this was recognized, I think, by Shebelin and collaborators, that these equations, the resonance conditions, imply that either K1Z or K2Z must be 0. So this is the interaction with zero mode that was probably referred to by Sergei. Okay? It's similar anyway. So which means that if I have a positive packet interacting with a negative packet, it interacts with something which is nearly a zero mode. Okay? So which also means that the positive packet cannot change its scale in the parallel direction. It scatters off a negative packet but retaining the same positive, retaining the same scale in the parallel direction. Which means that, one, there is no cascade of energy in the parallel direction. Whatever scale is there present initially when you stir it remains so, while there is a cascade of energy to smaller scales in the perpendicular directions. So turbulence must be anisotropic. All these things, this sort of stuff was broadly, was recognized by Shebelin, others. I'm only quoting, let's say, what I think are original references, okay? There's a lot of work done by a lot of people, and in case I missed out something, please point out, okay? So you'll find very few references to this. So this much was recognized in the 80s, okay? But not, to my knowledge, nothing quantitative, even at this order of magnitude level, was ever done. Much later, a theory of weak three-wave MSC turbulence was developed. Alright? Now, this is based on the notion that there is no parallel cascade. Okay? That at least the attempt is to modify Eroshnikov-Creighton theory to an extent that anisotropy is included. That's the main attempt. So when that is done, you go through this same business of wave packet collisions, but now you consider elongated wave packets. Wave packets extended, whose parallel scales are of orders of stirring scales, but with arbitrary transfer scales. So there's a cascade in the perpendicular direction. Go through the same sort of, phenomenology of considering perturbations in a single collision, then add up collisions with random phases, and then work through an expression for the cascade time, use Kolmogorov's hypothesis, and then you find that the RMS velocity amplitude now scales as lambda to 1/2 instead of lambda to 1/4. Okay? So self-consistency should again be checked in any theory of weak turbulence, that n sub lambda should be much larger than 1. Okay? So you work this out and then you find that n sub lambda is now proportionate to lambda instead of being proportionate to 1 over square root lambda. Which means that as lambda decreases, n sub lambda decreases, so interactions actually strengthen. So you start with the Eroshnikov-Creighton theory, you find that it's self-consistent, so hence you seek a rigorous description using kinetic equations. Then you find you have to satisfy resonance conditions, which imply that there is no parallel cascade. So you try to now include that. It's the business of anisotropy. Work through a phenomenology, and then you find that if you started out with very weak perturbations, as you get to smaller and smaller transfer scales, a single collision can get very strong. So, a theory of weak three-wave turbulence is sort of self-limited in scale. Okay? There is some small transfer scale at which the theory will break down. So, it must become strong turbulence. So let's see what happens. So you try to construct a theory of strong turbulence. So again, it's impossible to construct a rigorous theory of strong turbulence. So we go phenomenological. So we imagine that there is some very weak excitation, which strengthens as you go to small transfer scales. And at some scale, n sub lambda becomes order unit. Okay, and at that point, you have this, well, it's not so easy to argue logically what happens to n sub lambda. Okay? So at some point, while arguing that n sub lambda can it be less than 1? Doesn't make sense. Okay, that in less than 1 collision, things change by order unity. So at some point, Goldreich and I sort of try to make some progress by assuming that whatever happens on much smaller scales will be such that n sub lambda remains of order unity. That there is a balance between the wave period and the cascade time. That the wave period will be of order the cascade time for all smaller scales. Alright? So we set n sub lambda equal to 1, and then now we allow the parallel scales to also decrease. Why? Because the parallel scales were fixed at the stirring scales only when the three-wave resonance conditions were in force. That implies weak turbulence. But when you do strong turbulence, the parallel scales can now decrease because there are no resonance conditions. It's almost as if you are in principle using all orders of perturbation theory. And all of it is sort of hidden in this assumption that n lambda is of order unity. Excuse me, I'll just get some water if I can. Alright. It's okay. Alright, let's go on. So we've introduced this new quantity, big lambda, which can now be a function of the transfer scale. So what I mean is the following. In weak turbulence, you start out on some large scale, stirring on some large scale. As you go down to smaller scales, this remains there, the parallel scale, while energy cascades to smaller and smaller transfer scales. Alright? What happens in strong turbulence is that we stir on some large scale again, there, but allow the parallel scale to sort of change. Well, this is the transfer scale. And big lambda is a function of little lambda, which has to be now determined. So this is again quite easily done. We just go through the same arguments. Insist that n sub lambda is unity. Use Kolmogorov's hypothesis. And then you find that in the inertial range of strong MHD turbulence, V sub lambda scales as lambda to 1/3, and the parallel scale is now proportional to the transfer scale to power 2/3. Right? So which simply means that as you go to smaller and smaller scales, the radii are essentially more and more elongated. You get skinnier, okay, while getting smaller. So that's what strong MHD turbulence looks like in the balanced case. That is, there is equal amount of energy in the positive and the negative waves. Now, when you look at something like solar wind, okay, there is much more energy put out in waves which are outgoing. Okay, so clearly, I mean, one has to deal with the imbalanced case. People have worked on it. Now, people have worked on the imbalanced weak case, okay, where you have wave packets perturbing each other very little, I mean, not very much per collision. Perturbations build up randomly. Okay, so it's a weak case, but then there's much more power in the positive waves, let's say, than the negative waves. I'm not going into it. It's a pretty tricky case. Okay, I thought it had been settled, but I think Sergei has other thoughts on the matter. Okay, you catch him if you want to know about the imbalanced weak MHD turbulence. I'll go to the strong case. Strong, let's see, okay, imbalanced strong MHD turbulence. Okay, now we imagine that there is much more power in the positive waves than in the negative waves. Okay, and we also wish to describe a cascade which is strong. Okay, so let's see what the features are. There is a very general result. Just going back to the original Elsasser equations. Thank you. The result is the following. That, I mean, you take the Elsasser equations for the perturbations, take the equation for del del D of W plus, take a dot product with W plus itself, integrate it over space. So what you have is, let's say, the energy in each of the Elsasser fields. It turns out, it's very simple to check. It turns out that they are conserved. So if I have a lot of energy in the plus waves, very little energy in the minus waves, collisions will perturb each one of these. Okay? The minus will perturb the plus perturbs the minus, but they don't exchange energies at all. It's rigorous. So long as dissipation, I mean, you've dropped dissipation. So this is true in the inertial range. So what collisions do? In all cases, weak, strong, balanced, imbalanced, what collisions do is to redistribute energy in k-space. Alright? So if you put a lot of energy into a positive packet, all the energy stays in the positive packets. Okay? Now, so this is important to keep in mind. So let's again try to work through this phenomenology of imbalanced strong turbulence. I'd like you to imagine that there's a lot of energy in the positive packets. The negative packets are very weak. Okay? So clearly, the negative packets being disturbed by the positive packets will cascade very strongly. Each collision is going to sort of perturb a negative packet very strong. Okay? There's a parameter you can construct which measures the strength of this perturbation that a negative packet suffers. Alright? And you can think of it this way. positive packets bend field lines by this amount, W plus divided by BR fin. Okay? So the negative packets see such bent field lines. So they move along that. And when they move along it a certain distance, let's say the size of the positive packet, which is what? Okay, yeah. This is how much they are sheared in the transverse direction. So if they are sheared in the transverse direction by a quantity which is much larger than the transverse scale, then clearly the perturbation is strong. Alright? So that's what this parameter chi plus tells you. So when chi plus is less than unity, you are in a regime of imbalanced weak cascades. We are dealing with strong cascades, so we'll assume that this is larger than unity. So let's look at the negative cascade. Okay? You have a strong positive packet encountering, let's say, a weak negative packet. So by the time a negative packet sort of slides like this, it's already cascaded. Its perturbation is, the perturbation is very strong. Right? Therefore, the negative cascade time is simply the transverse scale divided by the amplitude of the positive packet. Hence, and over this time, the negative packet travels a distance which is B alpha times the cascade time. So that gives you the parallel correlation length of the negative packets. Alright, which is big lambda minus.
So is the positive packet stronger than the negative? Or
Yeah, I'm assuming that it's much stronger, say. Try to imagine an extreme limit. Yeah. So till now, I've not said anything about what happens to the positive packet. Alright, so I want you to imagine that nothing much has happened to the positive packet. Negative packet just slides along it. It gets sheared in the transverse direction. And these are, that's a cascade time and that's a parallel correlation time. Alright? So now, okay, now we look at the positive packet. So describing, let's say, the negative cascade is pretty simple. It's like strong turbulence. Alright? The positive wave cascade is much more tricky to imagine. So we asked the question, I mean, now, can the positive cascade be weak? So to answer that, we have to settle something about the parallel correlation length of the positive packets. Alright? Now, a positive packet will clearly have to encounter many negative packets, suffer many collisions with negative packets before it can cascade. Right? So, the first question to ask is, what do the negative packets do to the parallel correlation length of the positive packets? Okay? It turns out that even though the negative packets are very weak, they imprint their parallel scales on the positive packet. They may take a long time doing that. Okay? We imagine a steady state situation, not something where, which is the initial value problem. Okay? So there'll clearly be transients and things like that. But in a steady state, a positive packet is hit by many negative packets, and the correlation length of the negative packets is imprinted on the positive packets. Alright? Over a cascade time. This is a long time. So, we must have the parallel correlation length of the positive packets equal to that of the negative packets. Right? And henceforth, I'll assume that we have a common parallel scale, which is just big lambda, which is a function of transverse scales. Now you remember that chi plus, which is a strength parameter, okay, was taken to be equal to or larger than unity. Okay, but because they are the same, it turns out that chi plus must be about a unity. Hence, the negative cascade is actually critically balanced. This, by the way, this does not imply critical balance. Because what happens? A W plus occurs here and a lambda minus is there. But once we know that they achieve a common parallel scale, it turns out that the negative cascade is critically balanced in the sense the cascade time of the negative waves is such that, or rather, the negative waves will cascade by the time they go through one positive wave. Right? So how about the positive cascade? I mean, the cascade of positive waves. Now that's really tricky. But I'll give you the answer. The result is really boring. It turns out that the positive cascade time is simply transfer scale divided by the amplitude of the negative packets. Now this is a pretty boring result. Okay? And people have guessed such a result even in the isotropic case, just on dimensional grounds. Okay? But to actually derive that result turns out to be quite tricky. Okay? So let me just tell you why it's sort of tricky. The first question is, if that is the positive cascade time, it means the following, that negative waves, which can only strain positive waves by this amount, straining rate, okay, have to impose this strain on the positive waves coherently over a very long time, okay, which is the same as that. Okay? Because W minus can be arbitrarily small. We are assuming very weak negative packets, right? So that's what it implies. That's what this result implies. Okay? I'm just trying to point out that the boring result actually implies something very interesting. Yeah?
What do you mean is coherently?
Coherently in the sense, it's not like in the weak case where perturbations add with random phases. There's a long coherence time. Many negative wave packets hit a positive wave packet. Each one of those negative wave packets offers a straining rate which is W minus divided by lambda, which is a small straining rate. But the small straining rate has to be applied over a very, very long time. So there is some long-term coherence in the negative wave packets. That's what it implies. That's what the result implies. And I try to argue that the result, which also implies that the coherence time of the negative waves is much longer than their wave period, okay, should be understood as follows. It happens because of the following. Okay? It happens because in the frame of the positive waves, okay, I'd like you to imagine the following. It's tricky to say, sort of. In the frame of the negative waves, the positive waves, imagine negative waves hitting the positive waves, one after another. Right? The negative waves keep changing the positive waves, okay, by some small amount. Okay? And the positive waves back react on the negative waves. Okay? You have to go back and forth in this. So imagine that the positive waves are changing over some long time scale, which is tau plus. Okay? This tau plus turns out to be the correlation time of the negative waves which are hitting these positive waves. Alright? It's essentially due to this so in the frame of the positive waves, the negative waves change the positive waves, and then the positive waves act back onto the negative waves. Alright? So this means that the positive waves are changing on a long time scale, which is the cascade time scale. So over this time scale tau plus, negative waves actually see completely different positive waves in the frame of the positive waves. Okay, it's pretty tricky. I mean, I don't know if I'm making sense, but I'm open to discussion on this. Okay, this can actually be estimated. Okay, that if you put negative waves in on some large scale, okay, if the positive waves are not changing at all, the negative waves will maintain that long correlation time, which could be infinitely long. It's only when the positive waves sort of change do they impose their correlation time, their time scale on the negative waves. Okay? And this is what ultimately determines the positive wave cascade, okay, which turns out to be strong. Strong in the sense that it's not critical balance where cascade time is of order the wave period. But it's more, the cascade time is of order the correlation time. The cascade time of the positive waves is of order the correlation time of the negative waves in the frame of the positive waves. Okay. Now this is how best I can say it in a couple of minutes. Okay, but we can go through a sort of detailed estimate where we can put in negative waves, imagine that they cascade, and try to estimate this correlation time. I better stop here. Got this. Open to questions. Let's say, okay, results. Okay. So when you do this, okay, I should just quote results. Both W plus and W minus scale as lambda to 1/3. Okay. The parallel correlational length again scales as the transverse correlational length to power 2/3. Okay. This has the property that the ratio of the RMS LSSR amplitudes is independent of transverse scale. Okay, and is equal to the ratio of the corresponding energy fluxes. So it's a sort of prediction, okay, which can be checked. I mean, you measure the energy fluxes, you can say something about the amplitudes. Can be checked perhaps in simulations, perhaps in the solar wind observations if people can check. The rest of the properties are almost the same as the balanced strong cascade. Really crucial physical difference is that the cascade time of any one of the waves, the negative waves, let's say the cascade time of the negative waves is equal to the correlation time of the positive waves in the frame of the negative waves, and vice versa. Okay. So of course, in the limit that the energy fluxes are equal, the turbulence becomes balanced, things are okay. Right? Stop.
I have two questions. In the MHD turbulence, would you be able to perform similar analysis by including shear flow?
Shear flow?
Yeah, if you have shear flow, they will alter your resonance condition and they may also alter your cascade timescale.
Perhaps. Yeah.
And the other question is, I'm not very well aware of the similar analysis in the case of rotation and in the stratification. In the rotating system, you will have the extensional inertial waves, which are kind of similar to alpha waves. The effect of rotation is very similar to the effect of magnetic field. You will have different waves in this strongly stratified medium. Are there similar analysis during this kind of waves?
Okay. It's true that by and large there is always some analogy between rotation and magnetic fields, but I don't know if inertial waves have this property. They're only oppositely directed. First of all, whether you have waves which translate uniformly in the plus and minus directions, and only oppositely directed waves interact. I don't know if they share this property. I don't think so. So alpha waves are very special in this sense. Okay, and this whole picture is built on ultimately on Kriegmann's sort of insight. Okay. Otherwise, the whole thing falls apart. Or rather, the physics will be very different.
Other than what? Looking at the wave turbulence.
Sebastian goes with quick picture.
Yeah. Big turbulence of inertial waves.
Volcan Bone and Fabian Mallet, Wilson. Okay, stratified. Both Zeitlin,
Yeah.
Simulations are being done or to check by anybody that you know?
Well, I mean,
They're
okay.
welcoming people to do it.
Yeah, I hope people will do it.
So imbalance, I didn't understand. Imbalance, I would have thought just the flux of positive and negative are different. But you also have somewhere used the positive wave. A wave packet is stronger than the negative
True.
wave packet.
And the first point.
Oh. Okay.
So, you know, in the weak case, right? So what you consider very strongly imbalanced, right? So that to make the picture more sort of extreme and easy, more transparent, right? So to say. In weak case, when you go to that extreme, right? So there's a kind of window of locality which you go outside of. So in other words, so one spectrum is becoming shallower, another spectrum is becoming steeper. Say plus waves shallow and minus waves steep spectrum.
Yeah.
And at some point, actually, the interaction becomes non-local.
Yes.
So if you try then to use scaling argument based, like, like Kolmogorov, based on just the scale you are sitting on, that is not going to apply anymore. So you're going,
In the weak case.
in the weak case, but
That's true.
don't you think you expect here a similar kind of thing? I mean, if you're very strongly imbalanced, your one spectrum is much steeper than another one,
Yeah.
right? And then the one that is less steep is actually interaction in it is non-local, because the steep spectrum is seen as simply just a spike at large scale.
Yeah.
Spectrum.
Okay. See.
So if that's true, then actually you can say something rigorously there, because if you have scale separation parameters, you're becoming essentially like a passive scalar problem in bachelor regime, so to say. And so you get this bachelor k-1 cascade spectrum. So as an extreme case of this very, very strongly imbalanced.
Okay, so, see, in the weak case, let's say you try to construct a phenomenological theory of imbalanced weak turbulence. You find that even at the phenomenological level, things are indeterminate. You can't really determine what the spectral indices are. You only get a constraint, I think, on the sum of the spectral indices. All right? When you try to construct a phenomenological theory. Now, my impression is that the way at least two different groups, one I think Litwick and Goldreich, another Cartier and others have constructed a theory of imbalanced weak cascades, where they get over this problem of indeterminacy of spectral indices by making this assumption, I think, maybe backed by experiments, that the spectra, W plus and W minus RMS amplitudes, equalize on the dissipation scale. In some sense, the spectra they claim are pinned at the dissipation scale. Now that's good enough to determine, to get another relationship, complicated relationship, to determine the spectral indices, and it's clearly sort of non-local, because you start with trying to describe turbulence in inertial range, and then you find that the value of viscosity actually determines, plays a role in determining spectral indices.
Well,
True, there is this.
I don't really agree with that.
Perhaps. No, I was just.
The ratio between slopes is very simply obtained in the weak case by the ratio of the fluxes. I mean, you are free to insert a particular amount of plus energy and minus energy, and the ratio of that will determine the indices.
Perhaps you're right, I don't know. Okay, I haven't thought about the weak case. But at least the weak case is something that you can settle by trying to derive kinetic equations, solve them numerically if possible. I mean, at least some amount of rigorous work can be done. And my impression is that Litwick and Goldreich did that. They set up these kinetic equations and solved them. I haven't really looked into the details of the solution. But what it means is the following. Okay, at least the lesson I learned from this is that you try to construct a phenomenological theory. You fail. No, sorry. Phenomenological theory of inertial range transfer, which is local. And then you find No, things can't be local, or at least things are indeterminate if you assume locality. So you have to expand your assumptions and then maybe say something like things equalize on the dissipation scale or something else. So suddenly you find you have to be non-local. The approach taken here is the following. We imagine something that's local in wave number space. Okay? Interactions between eddies or wave packets of similar scales. And all I can say is that with this assumption of locality, we are successful in being able to construct a phenomenological theory. I won't defend it any further. It seems all consistent, it seems very interesting that there is this correlation time of the negative wave packets, which is very long, which is unrelated to their wave period, and is determined by the cascade time of the positive wave packets, or you can say one determines the other. It goes back and forth. So at least it looks sort of consistent. Can't say more.
Dostan?
So your motivation was, for example, the solar wind, where you have
Yeah.
one dominant direction. And so the naive question is, okay, what happens if you don't have this negative wave packets coming in? And your answer is nothing. Everything, you don't have a cascade. So if you scale up the negative wave package, your cascade should get faster and faster.
Yeah.
So the question is how much, since probably most of the turbulence comes from the sun, the question is how much inwards moving turbulence you should expect. And in the case of the solar wind, I would guess that it is due to reflection of outgoing waves on expanding field lines, because you don't have a homogeneous background magnetic field, you have something which expands. So in your thinking, you can also describe this as an interaction of some very large scale mode with something coming in, and maybe calculate from that the reflection and then make a direct prediction of how much reflected flux you should have, and there, what is the turbulence escape time in the solar wind, because everything seems to be fixed.
Okay, I don't know if negative waves, let's say incoming waves and the ingoing waves in the solar wind are due to reflection of positive waves. It could be because, see, solar wind is pretty complicated in the sense that there are regions where there's collision between, there are shocks. Okay? There are regions of shear where there could be local instabilities, which could generate both ingoing and outgoing waves. So I don't know what the generation mechanism is. But independent of the generation mechanism, so long as you're looking on scales much smaller than the generation scales, okay, we at least have one prediction that if you're able to measure amplitudes as amplitudes of positive and negative waves, spacecrafts do that, in situ measurements are there. Okay, they can actually filter out ingoing and outgoing waves because they measure, velocities, magnetic fields, and then take W plus, W minus. They can do all that. These things are pretty routine. Okay? So you have a measurement of amplitudes, W plus, W minus, is a function of lambda over some range of lambda. And this is enough, if this theory as sketched out is right, is enough to tell you what the ratio of epsilon plus to epsilon minus is. Right? And it should also be independent of scale. The W plus by W minus should be independent of scale as a prediction of this. And the ratio should give you epsilon plus to epsilon minus. So it's something that can be checked.
Other questions?
Okay, one question is actually related to Torsten's question. So what do you think about the possibility of creating this oppositely moving package by parametric instability?
Can you explain that? I don't know what this parametric instability is.
So maybe if you have a compression, then you actually can change the output speed. and then you can actually create.
Sorry, I haven't thought about this. I mean, you're talking about generation or interactions in the inertial range. What do you have in mind?
No, I'm just saying that you can amplify this optically moving packet by this parametric instability.
I haven't thought about it.
And another question is that how do you think about pseudo-alpha modes or slow modes? Do they follow the
Pseudo-alpha waves. Okay, I should have said something on that. Now, as far as I know, they are sort of slave to the alpha wave cascade. The reason being the following. Okay? That as you go down the inertial range, all right. So let's say that's okay. So as we go down the inertial range, and then we are looking at packets which are like this, right? You find that let's say this is isotropic generation, and this is generation where the k vector. Okay, you can see that k parallel is much less than k perp in this.
Yeah, I think I know in the strong turbulence, balanced turbulence, basically slow modes follow alpha modes. I wonder if in this imbalanced case it's still the same.
I haven't looked at it, but I don't see why it should be any different. Because it's essentially based on the fact that the dominant wave vectors, the wave vectors which have a lot of energy, are those where k perp is much larger than k parallel. So you have a situation where it's almost like this, okay, where the slow is almost parallel to the magnetic field, and the alpha is perpendicular to the magnetic field. Interactions are essentially determined by, let's say, W dot grad, right? And W alphane dot grad, let's say, W alphane dot grad is the same as W alphane k perp, whereas W slow dot grad is awarded k parallel. So it's mostly determined by this. The dominant interactions are determined by the alpha waves. So you sort of think of the slow waves as being sort of scattered by the alpha waves. So again, we assume that it goes through here.
I think we have to stop now and do the coffee. Thank you again.